Welcome to this web lecture on k-means clustering. K-means clustering is a method that we can use to place facilities anywhere in the plane, as compared to the classic facility location problems that we've been looking into in previous web lectures, where we were restricted to certain candidate locations that we had to explicitly feed into the model. So let's look back into the example that we've been using throughout facility location as well. So Woodworks BV operates several sawmills which serve workshops throughout the Netherlands. And they're currently looking into opening additional sawmills in Belgium to serve the demand there. So what they would like to do, they would like to place K sawmills such that on the one hand side, each workshop is served from the nearest sawmill, and secondly, the squared distances are minimal. And we're going to look into why we're looking into squared distances in just a second. And one additional assumption that they're having is that they can believe that they can lobby municipalities to roughly place the facilities everywhere. So this, of course, is not always a good assumption. If it's not a good assumption, then classic facility location models with discrete candidate locations is definitely the way to go. But if we're looking really into the green field where we can place everything everywhere, then this is a very good assumption. So now let's look into why we're actually looking into a quadratic objective. So if we're looking into this setup, so we have a sawmill here and we have the workshops here and here, we have a total deviation of 1 and we have a squared deviation of 0.625. If, however, we're looking into the total into this setup, then we also have a total deviation of 1. So by total deviation, these two are not differentiable. But if we look into the squared deviation, then this one is clearly better than this one. Analogously, we could, of course, compare this one here to a second setup where we have 0.5 and 0.25. And then those two would once again be the same if we look into the maximum deviation, but we would see differences with respect to squared deviation. So quadratic objective just has the benefit that we're sort of balancing between just looking at the average and just looking at the maximum. So it just gives us a good middle ground of sorts. So now we're going to look into a heuristic for solving this problem. A heuristic is a well-defined intelligent procedure that allows us to find an approximate solution to an optimization problem. We also have exact methods. Those find optimal solutions, but our heuristics may not actually allow us to find an optimal solution, but just a solution. So a heuristic, if we bring it to the point, is an algorithm that finds a solution and is not necessarily optimal. Then, of course, we quickly need to understand what an algorithm is. And an algorithm is a systematic procedure that, in a finite number of steps, produces the answer to a question or the solution of a problem. So it's problem-based, it's an unambiguous set of instruction, and it terminates eventually. We're using those heuristics because they're faster than exact methods, optimality is not necessary, and some heuristics result in easier to understand solutions. So I would say in this case, this is not actually true, but the main reason in case of the k-means clustering is that they're a lot faster because due to the quadratic objective, we don't actually have the option to just throw it into Gurobi. So let's look into an algorithm that allows us to do this, and this is the Lloyd algorithm. So we first choose k arbitrary cluster centers, so we just place our k clusters somewhere. Then we assign each node to the closest center, and then we calculate the new cluster centers as the mean of everyone who was assigned to this location. And then we iterate from there until the cluster centers don't change anymore. So let's look into an example that makes it a little bit more approachable. So let's just say these are actually the data points that we're having. And now we're just placing two arbitrary cluster centers and we're placing them here and there. Now we're assigning all the nodes to the closest cluster center in step 2. So this makes those up here blue and those down here green. So now in the next step, we calculate the average location in there. So the average location of all blue ones, if we have these coordinates, is given by this function. So we add up all the x coordinates, 0, 0.8, 4.1, and 5. And we also divide this by 4, and we also add up all the y coordinates, so 0, 1, 4.8, and 6.1. Divide that by 4, and that just gives us this location of this new blue node. So we move the blue node. We do exactly the same for the green node. And now we can continue from step 2. So now we assign all nodes to their closest cluster center, which gives us this, this setup. So quite a few of the nodes actually change their color. So next step is we're shifting those cluster centers again by calculating the average. For the green one, that already looks quite good. For the blue one, it's actually still quite far up here because this node is still in there. So now we can continue from there. We reassign the green one. This formerly blue one becomes green and is being added here, while the blue ones only refer to this cluster down here. So now we move the cluster centers, and from here we actually see that nothing changes anymore, and we terminate. So this is the entire magic of the k-means clustering, and what I would like you to take away is continuous location, why we're doing it, when it makes sense, the benefit of square objectives, and I would like you to remember what the Lloyd algorithm is. Thanks.